Apologize for the delay here, just trying to get all the technology stuff working, which is not easy. I don't know for sure if it'll let me show you guys the video. Let's try if I do that video. Yeah, I think that's gonna let, at least you can see a human at some point. This here. Let's see how that works. Let's see if you guys will be able to see that at some point. Hopefully, you'll be able to see those when I need to get you to that point. All right. A couple cameras going. Just for the kiddos that are absent, we're going to need to have video for this. So, all right. Can you see? I can't even see what you can see right now. Can you see? Yep. Okay. That's a funny view, but there we go. There you go. You can see me, I guess. All right. Here we go. So, boom. Yeah, let's go. All right, so well, hello everybody. We're going to be talking about section 12.1 today. What is a solution and what isn't a solution? The idea here is that, solutions for me are a real frustrating topic because there's so many variables to it that it just kind of drives me crazy. But what I'm going to do is I'm going to show you the standard acceptable, book definitions of things, and then we'll talk about all the exceptions. I feel like there are more exceptions than there are rules when it comes to solutions. So our objectives today are to articulate the general the general properties of solutions, and then to describe the differences between solutions, colloids, and suspensions. And that's the part that really starts getting me crazy. So when we're done, I expect your successful criteria to be that you would be able to distinguish between a solution, a suspension, and colloid based upon the criteria that I give you. And then, of course, you'll know that there's lots of exceptions to those. And then the other thing about solutions is they're made up of two things, a solute and a solvent, but it can be kind of confusing to figure out which is which. So we're going to make sure that by the time you're done, that you can come out of here knowing which is a solute and which is the solvent. So first of all, you guys have seen these types of mixtures for years, right? Like you are very familiar with these definitions. However, they're still a little bit ambiguous when it comes to figuring out which is which. And that's because the criteria by which we decide which is heterogeneous and which is homogeneous sometimes are shown to be different in different textbooks. So what we're going to do here today is we're going to talk about the way that we want you to determine whether something is heterogeneous or homogeneous. And its tool that you're going to use is your naked eye, okay? So for a heterogeneous substance or mixture, you're going to be thinking of things that you can see the difference between with your naked eye. Now, a suspension would fit into this category. A suspension is typically going to settle down to the bottom, right? So we have a material here, and you can see the sand that is in here, okay? And the sand quickly, you can mix it up, but it's going to settle down, and it's going to be in two different phases. So heterogeneous mixtures have two different phases, and it's easy to see, okay? So that's one situation. A saturated solution also could fit into this category. For instance, I've got some baking soda here. Now, baking soda, if I put a little bit into water, it's going to mix in, but it doesn't take too long before it's saturated. So you can see some baking soda at the bottom here, and you can see that if I stir it up, I get this, mixture that's pretty uniformly, looks, at least to the naked eye at this point, uniformly mixed in. I can't see like anything settled, but if I wait for a little bit, there's going to be some of that baking soda that's going to settle to the bottom. And so we're going to end up having a saturated solution that will now fit into the category of a heterogeneous mixture because it settles down and I can see the two phases. Okay. Now, colloids. Do colloids fit under heterogeneous or homogeneous mixtures? We want to kind of work our way through that as we're talking about this concept. But the thing that you need to kind of remember is that a homogeneous mixture is synonymous with, a homogeneous mixture is synonymous with a solution. Okay, so basically, if it's a solution, it's a homogeneous mixture. So colloids, do they really fit into that? They look, colloids look as if they have one phase, but they have what's called the dispersed phase or the dispersed medium inside another phase, right? So it's kind of like, yeah, they look like homogeneous, but are they really? But the colloids typically look as if they have one phase, but they'll actually have two phases that are kind of intermixed and interspersed. A supersaturated solution, by the way, would be, the same kind of situation that we'd have for a homogeneous. It's going to be a solution, right? If we say that it's supersaturated, it is still considered a solution if it's a supersaturated solution. So that would still be considered a homogeneous mixture until the point at which, it is no longer in its supersaturated phase. And once it, settles out and it suddenly crystallizes, then you would have something that might fit into a different category at that point. So solutions have a single phase. And again, why are colloids not considered homogeneous solutions? Well, we talked about the fact that they seem to have one phase, but they actually have small little variations that will cause light to scatter. And so those small little variations we use to determine that they are not a homogeneous mixture. But you're not going to be able to really see the difference until you actually apply another test to it. So we'll talk about that test. All right, so let's talk about the parts of a solution. A solution is made up of a solute and a solvent. Now, when we use the term solution, we're kind of talking about something that is a noun, right? Whereas something that is soluble is an adjective that is describing something that is going to be dissolved, right? So something that's soluble is going to be able to be dissolved in something else. They're going to be able to mix with something else. And so the soluble substances are those things that we would use that word to describe their characteristic property of being able to be in a solution. Okay, so a soluble substance is something that can become part of a solution, right? And the solution itself is the noun that is describing a mixture of a solute and a solvent. Okay, so this is going to actually be the mixture of the solute and solvent. Now, the solute is a substance being dissolved, and the solvent is what's dissolving the solute, or what is doing that dissolving. Now, the tricky part about figuring out what the solvent is you don't necessarily know what is in the greatest amount, because it's tricky sometimes. Let's say I had 250 grams of sucrose, and I was dissolving that in 150 grams of water. Now, in this case, you'd be like, well, 250 grams is more, but it's not. If you're actually looking at how much the water, has in terms of moles and how much the sucrose has in terms of moles, the water is going to be in a greater molar amount, even though it has a smaller number of grams. And it might have a smaller volume too, but it's still greater in the molar amount, how many moles there are. And so the water in this case would actually be considered the solvent, even though there's more sucrose. So when you decide what a solvent is, make sure you figure out how many moles each of them has, because it's the number of moles that's going to determine whether or not one is a solvent or the other. Now, I will tell you that, you could have something where like it's an alcohol and water mixture, where these things are commiscible, meaning that they are infinitely dissolvable in any amount of a particular substance that they have. And so in those cases, then you would be justified at saying that this alcohol could be the solvent sometimes, and then the water could be the solvent sometimes, depending upon the ratio of alcohol to water that you had. All right, so in this particular example here, we can, oops, go back. I wanted to show that to you. We can see, for instance, maybe this is like copper 2 sulfate dissolving in water to create a new solution, right? Which one would be considered soluble in this case? Would be the solute, right? The solute would be considered the soluble thing because it's going to dissolve into the water. Okay, so not that water can't be soluble, water could be soluble in alcohol. But in this particular case, the solute, the copper 2 sulfate, would be the thing that is soluble in the water in the solvent. Okay, and then that creates that solution. Okay, so let's look at, we've got about 4 different criteria here that we typically use to try to figure out what our mixture is. Is it homogeneous or heterogeneous? Is it a suspension, a solution, a colloid? These are our test tools, basically. Okay, we have the Tyndall effect, we have filtration, we have particle size, okay, and then we have whether or not it can settle out or separate. Now, these are our tests, right? We can use these tools to determine if something is going to be a suspension, a solution, or a colloid, okay? The Tyndall effect is used to tell us about whether it's going to be a colloid, okay? If we see the Tyndall effect, we can say, oh, that's going to be a colloid. But there are so many different variables, and I'm going to show you that here in a second. There's so many variables that will help us figure out whether or not the Tyndall effect is even happening, the type of light, the concentration of the substance, that we really have to do a good job of figuring out, what variables do we really want to talk about? And I don't think that the texts are very clear on that. Filtration. You normally would use a filtration system to determine if something might be a suspension, right? So if it's a suspension, the suspension should have substances that you could filter out. Well, yeah, like if I had the sand, right? If I had that sand in water, I could definitely filter out the sand. But really, really, really good filters might be able to filter out something that might be even finer, right? Might be able to filter out like tiny little variations of small little sugar particles, let's say, that are dissolved into water. So if I had a super good filter, that I would normally say a sugar water solution is a solution, but now if I get really good filter paper, now it can filter out. Does that make it a suspension? No, it doesn't. So we really need to have some criteria, and I think the text should probably talk about what criteria we would use to take and say that something is a suspension based upon filtration. And part of that is going to be the size, right? Suspensions are supposed to have particles greater than 1,000 nanometers. So if a particle is greater than 1,000 nanometers, then we can usually call it a suspension. And so we got to say, well, the filtration paper probably needs to be something then that will filter out things 1,000 nanometers or bigger. Okay, if it filters out, something smaller than that, then that's going to go a little beyond what we need to do for suspensions. So those particle sizes are varying greatly, even between a substance. For instance, like if I were doing cornstarch has long chains of carbohydrates and short chains of carbohydrates. So if I had a mixture of cornstarch, I might have some big pieces and some small pieces. The particle sizes can vary depending upon if it's a polymer, how big those pieces of polymer can be. So particle size are crazy different too. But in general, when we talk about particle sizes, less than 1 nanometer is going to be a solution, okay? And then if it's between 1 nanometer and 1,000 nanometers, we would call it a colloid, okay? And again, so one of those definitions, things that we look at is the settling out, okay? But what if they separate by polarity? Okay, so here I've got a mixture of oil and water. You can see a small little layer of oil right at the top there. Now, that is settled out, and the water is on the bottom, and the oil is on the top because the oil is less dense. And so we can see that it's a homogeneous mixture for sure, right? But we can't use particle size to determine how these things are separating out, because those particles of oil are not necessarily smaller, right, than 1,000 nanometers, but they could be smaller than 1,000 nanometers. So if those particles of oil are smaller than 1,000 nanometers, in this case, they probably are, but those are still separated out, even though they're, you know, typically not big enough to be a suspension. So there's lots of little variations that happen here. Okay, and so that's why we kind of really we need a lot more guidance from text and from the scientists on how to determine these different categories. And it's a vague. It is vague, and so I'm teaching you what you need to know, but it is kind of frustrating. All right, so let's talk about the Tyndall effect. And as we talk about the Tyndall effect, I'm going to have somebody kill the lights. And this will give us a chance to look at the Tyndall effect a little bit better. Okay, so this is a property that's used to distinguish between the solution and a colloid, right? If you can see the visible beam, then we consider it a colloid. And if we can't see the visible beam, then it's considered a solution, okay? Again, the idea here is that as the beam is traveling through a colloid, it's going to cause a scattering of light because of the particle size, and it's going to shoot the light up to our eyes. And so we should see the beam actually traveling through it. I give you a little picture of it there, but I want to show it on the camera as well. I see we do have a question in the chat that asks about gases trapped inside solids. Yes, it's still considered a mixture. And yeah, if you can't see the visible difference between them, then in this case, we would still consider that homogeneous mixture. Okay, actually, I'm going to close my blinds here a little bit so that we can see this a little bit better on the video. Too much residual light coming in there. Okay. And I'm going to point this camera down and that camera down. Hopefully this will make it so you guys can see it. Okay, so let's look at some of the solutions that we have, and let's see if we can see the Tyndall effect. Now, I'm going to show you the Tyndall effect is most visible in a gelatin. Okay, gelatin is great for demonstrating the colloid effect, or the Tyndall effect, and it's great colloid. And this is the one right here. All right, so if you look here, you should be able to see the Tyndall effect. Now, I've got a regular flashlight. You can see the beam as it's traveling through. My hand might be a little bit in the way there. If I show a laser light, you can see that a lot better, okay? Can you guys see that on the screen? Is it visible, laser? Okay, so you can see that laser moving through. That's the Tyndall effect. Now, again, if I just do regular light, not maybe quite as easy to see, but you can see the beam still moving through, right? We've got that flashlight's got a kind of a focused beam. You might be able to see that one halfway decent there. But it's also kind of fun to look at other types of lasers. I've got a green laser here, and you don't see it very well, okay? But I also have a blue laser, or purple laser, and this one you can see really well. Isn't that fun? So you can see that purple laser really, really well. Now the thing, and again, that's gelatin, so it's a great example of a colloid. That's your like prototypical colloid example. But if we look at some of these other substances, we can see that some of them, you know, can show the Tyndall effect as well. Now this is just regular tap water, but I got the tap water is not exactly, you know, been filtered through great, so you can see the Tyndall effect, and there's plenty of particles in there. If you take some of these other solutions, you're not going to be able. You're not going to be able to see them quite as Well, that one we say is a solution. Can't really see that laser light through it. But let's look at the purple laser. Can we see the purple laser through there? Yeah, you can. So you see why I think that the Tyndall effect needs to have some greater criteria to decide whether or not the Tyndall effect is being shown. What kind of light are you doing? What's the concentration? So for instance, here is that baking powder. And, it's settled down a little bit now. So now can I see that laser light pointing through? Yeah, I can see it going through. Milk is typically used as an example of a colloid, but this milk is too thick to actually even let the light pass through it. Okay, but if I take just a little bit of that milk and I put it into, another substance, and I let that milk, and I just put like a couple drops in it, and I mix that in, then that can actually work pretty well to show the Tyndall effect, right? So, it doesn't take very much. Like the colloid here, the concentration is too great to see the Tyndall effect because the light can't even penetrate. But if I just take a couple drops and I put it in, now I can see the Tyndall effect. And so I can see that those particle sizes were probably about the right size to demonstrate the Tyndall effect, right? Food coloring. In this case, if I shine the laser light in the food coloring, can't really see it at all. But again, if I use my purple laser, ooh, this one I can't really see. So this yellow food coloring, I can't really even see the purple laser going through. So that's interesting. And yet those particle sizes of those pieces of food coloring are probably pretty significantly large. If I look at my sand, we'd normally say, oh, this is definitely just a suspension because of the sand falling through, but yet the purple laser shows through it pretty easily. The red laser even shows through that sand water, right? So there can be tiny little particles that were mixed in the sand, and then that makes for some substances that can be in that water that'll show, the laser showing through. But does a regular light shine through and give you the Tyndall effect? No, the regular light doesn't really give you the Tyndall effect, but the laser does, right? So again, there's so many different little variables that you got to talk about when you're talking about whether or not you observe the Tyndall effect. You can see a little bit of it with the blue light. Might be hard to see there, but you can't see all of it. So yeah, it's kind of interesting to look at those different types of solutions and try to figure out what they are. But it's definitely variable, and it's not something that you should think has got these boundaries with black and white. There's definitely a lot of gray lines there. Let's talk briefly about emulsions and liquid crystals, okay? Because emulsions are a type of colloid, all right? And basically, if you can take two liquids that they don't typically mix, they're immiscible, and you can get them to mix for some reason, okay, whether it be through physical processes, like homogenized milk. In homogenized milk, in order to homogenize the milk and take the fat and put it into small enough particles where it stays suspended in the milk, they shoot it through these they shoot the fat through these tiny little holes, and they make the fat droplets so small that they stay suspended, okay? You can also use chemicals to homogenize things, to make sure that the fat stays in a particular layer, or just stays within that same phase. Vinaigrettes, right? If you've ever had a vinaigrette, you can mix the oil and water for a while, and they'll stay mixed together for a little while, or the oil and vinegar. So if you can get things to kind of mix together that don't normally mix together, that's called an emulsion. Mayonnaise is considered an emulsion. But that's a non-ordered arrangement. If you will take a liquid crystal is an ordered arrangement of two liquids. And one of the good examples of this you might remember from biology. All right, in biology, you remember that there was something called a lipid bilayer. And that lipid bilayer is what's around all your cells, okay, and around some of your organelles a lot of times as well, right? So that is an ordered arrangement of oil. Okay, it's fat, but it's an oil, and that basically is considered a liquid crystal. If it's non-ordered, then it's considered an emulsion. And so there's these things, tiny little spheres called mycels, and they can be all different, sizes, of course, but those are considered emulsions versus liquid crystals. So emulsions are a big part of colloids, because when we look at different types of colloids, a lot of them are emulsions. Question about suspensions. Yeah, so typically, like if you had a bunch of dirt, mixed in with water, that's just basically going to block the light. A lot like the milk did. The milk was basically blocking the light, and that would basically be the same thing that your suspensions would do, at least until they settle down. And then you might see the smaller particles, and the smaller particles that are left in there might be like colloid particles. Now, you don't have to write this down. This one is just kind of cutting edge technology that I thought you'd be interested in knowing about. And this is microemulsions versus nanoemulsions. Now, these are, if you look these up online, you're going to see that these are being used in medical applications to, basically dispense medicines to inside your body, right? If we can create these are, you'll notice the size is below 100 nanometers. Right, so that still fits into the colloid, between 1 and 1,000 nanometers, right? So it fits into this colloid category, but notice that it says that they're translucent, right? So they're not going to be scattering light. So they aren't going to have the Tyndall effect from what I understand here. But they have two differences. The microemulsions they're basically easily compromised by diluting, heating, or pH changes, and so they're not quite as good. And they also have a lot of surfactants. The surfactants are the things that make them stay in solution. And so the nanoemulsions have lower surfactant concentration, and they're more stable. They have to use special equipment to create these droplet sizes at this rate, but those are what they're starting to try to use to distribute medicines inside your body. And nutrition studies and things like that are being done with this kind of stuff. So it's pretty cool. A little bit of a current research. All right, so let's kind of excuse me, summarize what we've learned up to this point and come up with some examples. So our suspensions, do they settle? Yeah, okay. Suspensions are going to settle. Can you filter them? Yes, you can filter them. And again, there's differences. Of course, we can talk about sizes of filters. Do they display the Tyndall effect? Again, what we'd say is no Tyndall effect. You either can't see the light going through, or they've settled out. And so, Tyndall? No, not Tyndall. They've either, they're too concentrated and you can't see light going through them at all, or they may have settled, and then theoretically there's no colloid-sized particles and you'd see no Tyndall effect. And if you did see the Tyndall effect, then you're having a colloid mixed in with a suspension, right? You've got two different things there. Particle size, again, remember they're greater than 1,000 nanometers. Perfect example here that we've given you is sand and water mixed together, right? Colloid, does it settle? No, it's not going to settle. Is it going to filter? No. Now, again, you think like, well, Jell-O is a colloid, right? And that definitely would, oops, it's not settled both times. And that would definitely not go through filter paper, Jello, right? That's a gelatin. So, but again, we're talking about the liquid-liquid situation here. The effect on light, definitely the Tyndall effect, okay? And again, lots of variables there. That's one of our criteria that we'd use. And it's between, the particle size is between 1 nanometer and 1,000 nanometers. Example, gelatin and water mixture is a great one. That's one we use a lot. Solution, settle? No, not going to settle. Not going to filter. And no Tyndall effect. And again, this one drives me crazy because, again, if you have like a blue laser or something, you're going to be able to see the Tyndall effect in typical solutions. And then what's the size? They're less than 1 nanometer particle size. But, if you look at, certain solutions like sugar, if I had sucrose, is a sucrose particle less than 1 nanometer? It's really close. You might be able to argue that there could be some solutions that might have particle sizes that are a nanometer or bigger than a nanometer. So typically we use salt and water is a great example here. Sugar and water is also a good example of a solution. Okay. Okay, so I have a question that asks about mud, where you have this mixture of the water and the dirt, right? Question says, could you argue that the water being evenly dispersed throughout the solid, being then a solution, since you can't see the difference between the two, and it's like a liquid dispersed throughout a solid. And so then, yeah, your dissolved particles, in this case being the water, are smaller than a nanometer and evenly dispersed. Yeah, I kind of like that argument. I think that is not a bad argument at all for mud being a solution. But again, yeah, can you shine the light through it? No, right? And so you're not going to necessarily see the definitely a suspension in terms of mud should settle because of its greater density. It should settle, and you'd end up ultimately, if you didn't have any evaporation, you could end up having the solid particles being down at the bottom and then the water being at the top. But if there's enough attraction between the mud particles and the water, maybe they stay evenly dispersed. Yeah, again, that's a great example of how these definitions don't necessarily don't work that great in all sorts of situations. Do want to talk about commissables. Now you'll notice that my title here says Powers proposed terms for mixtures not establishment approved. I basically have come up with my own little definitions of a lot of things. I'm not going to have you guys go through them all. I'm just going to zip through them because I think that they're kind of frivolous because I've kind of made them up on my own. But I wish that the scientists would start establishing some better terms that will help us understand some of the differences between these. But commissables is one that basically is accepted by science in general, and these are things that are basically mixed together at any level of mixture. Okay, they stay mixed at any concentration, and that's because they're attracted to each other. So it'd be like alcohol and water, things like that. Other terms that I have, like semi-miscibles, immiscibles is one that would make sense. And I think we should have terms like a Tyndall concentration, a Tyndall intensity, Tyndall frequencies, Tyndall light variables, things like emulsions, miscemulsions, all sorts of stuff. But again, that's all kind of frivolous and fun. If you'd like to see that sometime, you're welcome to come talk to me about them, and I'll tell you what I think we should be naming some of these things. All right, so let's look at some of these different types of solutions that we have. We have a gas and gas solution, and these are always commiscible. They're infinitely mixed in each other, and that is oxygen and nitrogen. Okay, in air are going to be commiscible, right? They're going to be a solution of gas and gas. If I have a gas mixed in a liquid, a great example of that would be your carbonated beverages, right? Carbon dioxide mixed in water, or chlorine gas in water from the swimming pools. If you have a liquid and liquid mixed together, alcohol is a perfect example of this with water, right? Those, you can have various different proofs of alcohol, different mixtures and concentrations. Vinegar and water would be another example. If you have a solid mixed in with a liquid, right, the liquid's a solvent and the solid's a solute, sugar and water or salt and water. If you have a liquid mixed in with a solid, a great example here is a dental amalgam, like the old kind of school fillings like I've got in my mouth, where you've got the liquid was put into the solid and it actually bonds to the solid. The liquid, the mercury actually bonds to the solid silver, and it creates a really great bond that doesn't actually leach out. And so mercury fillings, even though I've got mercury in my mouth, they are supposedly safe and are not leaching out. Then you have things like solids and solids. Now, Could you mix the silver and gold and 14 karat gold while it's a solid? No. You have to mix them while they're liquids. For the steel, you take the liquid iron, right, and then you put the carbon pieces in it, and then it starts to bond together. But by the time they solidify again, they get cooled down, then they're solid and solid mixtures. And these are solutions, okay? All of these that you're seeing here are solutions. And even though you can't shine a light through a solid substance, it still classifies as a solution because it's a homogeneous mixture, and you can't see the difference with your naked eye between, for instance, the silver and the gold and 14 karat gold. And so we still consider these solutions because there's no distinguishable difference that we can see with our naked eye. You just can't, do a Tyndall Effect test on them and have it tell you really anything of significance. All right, so these are just examples of liquid and liquid. So you can see that the ethanol is distributed throughout the water, and they're bonded to each other. And then you can see the silver and the gold are bonded to each other, distributed throughout that metal as well. Now, as we wrap up, last little concept we're going to talk about is electrolytes, because when we talk about solutions, there's a particular category of solutions that's important to us, and that is this category of electrolytes. Now, electrolytes are used in all sorts of things that they're important in our body for a lot of our functions, like our nerve functions and our muscle functions. And electrical conductivity requires ions, okay? And so we have to have the presence of ions, things like sodium ion, chlorine ion, right, from table salt. Those are going to allow for electrical conductivity. And so an electrolyte is considered a substance that dissolves in water and then gives a solution that conducts electricity. But some things don't. So you can have solutions that are electrolytes, and you can have solutions that are non-electrolytes. If I, dissolve salt in water, I would have an electrolyte. But what would happen if I dissolved sugar in water? Okay. So a sugar water solution is considered a non-electrolyte. That actually does not does not conduct electricity. So the sugar dissolves, but it doesn't conduct electricity. Now, the big key to remember here is that things that are made up of molecules are typically going to be the non-electrolytes. And the things that are made up of ionic compounds, okay, those are going to be the electrolytes. Okay, so molecular compounds are going to be non-electrolytes, and then the ionic compounds are going to be sorry, I don't know if I said that right. The ionic compounds are going to be electrolytes, and the molecular compounds are going to be non-electrolytes. Okay. All right. So you guys may have thought and heard about electrolytes before when you've had like Gatorade and things like that. Your calcium and magnesium ions that you might get from something like a Gatorade are the electrolytes that help your body function under the duress of sports and things like that. So let's see if you can predict the type of bonding, and therefore then also the type of conductivity that you would have in these substances. If we start with water, you've got H2O, right? And so if you have H2O, that's a molecular compound. And because this is a molecular compound, this is a non-electrolyte. And you're like, what? Because I could have swore that water conducts electricity. I've seen lots of movies, the hairdryer falls in the bathtub and the person gets electrocuted, right? Well, the thing that happens there is, remember, tap water is not going to be pure water. And so we want to talk about this water, and we got to say, yeah, well, pure water is not going to conduct electricity very negligibly at all anyway. And, if I put in a body where I have all the salts coming off of the body, and that immediately starts to increase the number of ions in there, or if I have tap water that, has a lot of ions in it, then it's obviously going to conduct electricity pretty easily. So pure water would be considered molecular, and it would be considered a non-electrolyte. Okay. And then come on, catch up with me. And then the glucose, again, this is a molecular compound. Okay, so non-metal combinations, right? So this is also a non-electrolyte. And then if we had calcium chloride, that's considered an ionic compound, right? You're like, how do you remember? I don't remember how to do that, Powers. Remember, if it's a metal combined with a non-metal, That's the quick and dirty way of determining whether it's ionic, right? And so if this is ionic, then that means that this is going to be an electrolyte. Okay. So that's how you tell between those. Okay, we have another question here. What are bubbles? Are they mixtures? Bubbles are considered a foam, which is a type or category of colloid because it's a type of emulsion. You have a dispersed medium, dispersed inside another phase. And so, you've got, there's a couple different emulsions that you can look at. And, for instance, you could have a gas dispersed into a liquid medium, or you could have a liquid dispersed into a gas medium. And in the case of bubbles, I think you've got the gas that's dispersed into a liquid medium. And so that's the type of emulsion I believe you have for that one. Yeah. So again, another example of a colloid. And what would happen if you shined a light through a clump of bubbles, right? Would you be able to see a laser light through that? I don't know. I haven't tried that one. That would be fun to try. All right, so let's check out our criteria for success. Let's see if we can do what we set out to do. Can we explain the characteristics of and distinguish among solutions, suspensions, and colloids? Yeah, now we know what basic things to look for, right? Solutions, that it is not going to show the Tyndall effect, for instance, right? Suspensions is going to settle. Colloids is going to show the Tyndall effect. We can look at those different types of tests, and we can do a quick and dirty test, and we can tell you what they are, although we might see that there's lots of different exceptions. And then, can we identify the solute and the solvent? Well, remember back to what I said. The solute is the one that's present in the least molar amount. The solvent is in the greatest molar amount. And so you have to look at how many moles you have of each. And if they mix, which one is present in the greatest molar amount, then that one is considered your solvent. Okay. All right. Well, I think that's all we're going to cover for today. So appreciate you guys listening in, and I hope you guys enjoyed learning a little bit about solutions, suspensions, and colloids.